what one number tells you. Whether an AI can undo what it just did or has destroyed your data forever. Watch this tile stretch and keep your eye on its area. That number is the area it now covers. And when it hits 0, space is crushed flat. Start with the unit square. Its two edges are the basis arrows I hat at 1 0 and j hat at 0 1 with a real picture painted on top. The matrix just records where those two arrows land. Its first column sends I hat to 2 1 half. Its second column sends j hat to 1 2. So the square skews into a parallelogram and the picture skews with it. A cookie cutter presses a shape into roll dough. The determinant is simply how much bigger or smaller the area it stamps out becomes. Here is the punchline. The determinant is not a random formula. It is literally the area of that parallelogram. The little unit square had area 1. This one has area 5. So this transformation multiplies every area by 5. And that area has a formula. The main diagonal times d minus the other diagonal b times c. 3 times 2 is 6. Minus 1 times 1. 6 minus 1 is 5. The area exactly. But this number can go negative. What could negative area even mean? A determinant can come out negative. Watch what that means. This arc curls from the first arrow to the second counterclockwise. Flip space with a reflection and the picture becomes its mirror image. The arc now curls the other way. And the math agrees. Minus 1 times 1 minus 0 is minus 1. Negative area means orientation reversed. And when it hits exactly 0, something is destroyed. Watch closely. Now, the dangerous one. A singular matrix. Here are two different points, A and B, and a whole cloud of data. Its determinant is 1 times 1 minus 2 times 1 half. 1 minus 1. Exactly 0, because the two columns point the same way. So apply it and everything, the entire plane, is crushed onto a single line. 0 area. A and B are now the same point. You cannot tell them apart, so you can never get back where they came from. That information is gone forever. This is a layer you cannot undo. Flatten a box into a pancake and you can never rebuild it. You have lost which crumb came from where. Determinant 0 loses information the exact same way. Add a dimension and nothing changes but the word. In 3D, the determinant is how much the unit cube's volume grows. Feed it a 3 by 3 matrix and the cube swells into a slanted box. Its volume climbs to about 3 1/3, the determinant. And if the determinant is 0, the box is squashed completely flat into a pancake with no volume at all. Crushed, just like before. So the sign tells you flipping and 0 tells you doom. What does a healthy, non-zero determinant buy you? It buys you an undo button. Because the area did not vanish, no information was lost, so you can always run the transformation backwards and land exactly home. And one beautiful law ties it to composition. Do two transforms in a row and their scale factors just multiply. Stretch by 3, then by 2, and space ends up 6 times bigger. Here is the picture that unlocks everything. Start not with a square, but with the unit circle. Apply the matrix and the circle becomes an ellipse. Every matrix does exactly this. It stretches space along two special directions. Those two stretch factors are called the singular values, the heart of the SVD. Multiply them together and you get the area scaling, the determinant, 1.8 from two stretches. This is exactly how PCA finds the axis of your data and how an AI sees which directions matter most. The idea is old. Leibniz and Cauchy saw it in the 1600s. Cauchy fixed the name determinant in 1812. And these two friends, Cayley and Sylvester, built the whole algebra of matrices around it. First, your data. Scatter a cloud of points and fit an ellipse around it. The determinant of its covariance matrix is that ellipse's area, one number for how spread out, how rich the data is. If that determinant collapses towards 0, your features are secretly redundant, all lying on one line, and models choke on it. The determinant is your redundancy alarm. Second, generative AI. A normalizing flow bends a simple blob of probability into a complex shape. To keep the total probability at 1, it must account for exactly how much it stretched each patch. That correction is the log of the determinant of the Jacobian. It sits right inside the loss the model is trained on. And the very same log-determinant appears in the likelihood of a Gaussian, the beating heart of VAEs and Gaussian models. This one number is everywhere in machine learning. So drop the idea that a D minus BC is some formula to memorize. It is a measured area. The one number for how much a transformation zooms space and whether it flips or destroys it. You can measure it yourself in a couple of lines. NP in log-det gives 5 for our first matrix and 0 for the singular one, the red flag that a layer just threw information away. The full notebook is in the description. Step back and see the whole season. Linear algebra, one reframe at a time, vectors, then matrices that bend space, then composing them, and today the one number that measures that bend. You are here. And why an AI engineer cares? A non-zero determinant is your undo button. The layer is invertible. A determinant sliding to 0 is a dead layer, collapsing your features and destroying data. And its logarithm sits right inside the loss functions models are trained on. We measured how much space stretches. Next stop on the map, how much do two vectors agree? That is a dot product, the engine behind similarity and attention. Next, the tiny operation that tells you how much two vectors agree, the engine behind similarity, attention, and every recommendation you have ever gotten. Thanks for watching and keep exploring. Next time, dot products and projection. Please like and subscribe ThirdEye Labs if you enjoyed this video and let me know in the comments.